between linear and nonlinear analysis of the structure. We will focus on the material and geometric nonlinearity and how it can be modeled, how it can be incorporated in our computer program. Then idealized model for simulating the nonlinear response. So there are three types of modeling that you can do to model the nonlinear properties of the material, or maybe at the member level or at the material level. So we will see that three models which is available. Actually, out of that, only two models we can use. That is lumped plasticity model in elasticity model and distributed elasticity model. So there are two distinct model which is available, and the third one, which is quantum model, which is highly accurate, but it is not available in ECAP. So we will see some of the features of this nonlinear simulating technique, nonlinear response simulating technique available in ECAP. Then regarding the performance-based design, we will just see some of the performance level defined by the different different standards like ASCE 41, then FEMA, maybe ATC, and their acceptance criteria. The ETAB hinge definition, which is for actually for nonlinear modeling. There are different types of hinges available in ETAB to perform nonlinear analysis. That is for columns, beams, and shear walls. So this is these three elements are basically the main elements where you actually model them as a nonlinear one, and then we can find out the response of the structure. And of course, what nonlinear model will give us, that is the output of our analysis. We will just overlook some of the output for push-over analysis, nonlinear time history analysis. So that is the broad outline for today's presentation. Just hold on. Yeah. So let me start. So let us start our discussion with some of the features, means some of the major differences between linear and nonlinear analysis. We have already seen this yesterday when we have done these linear things. But let us first focus upon this major differences between linear and nonlinear analysis. Linear analysis is displacement based, and the displacement relationship with load is linear. That means any force and deformation relationship is always linear. So even if you increase the force, the displacement will be proportional to the force. That means, suppose if you apply unrealistically high load on a particular structure, the program will return unrealistically high displacement, which is actually not there at the structure. The structure is yielded before reaching to that particular displacement. But because the relationship what we assume is a linear one, the program will return you a displacement which is also very high, and that is not realistic. Okay, so that is the major difference. Whereas in nonlinear problem, the force deformation relationship is always nonlinear, and the program will tell you which types of the member are yielded and which are still in the elastic range. So that is the first difference, the load displacement relationship. Of course, the at material level, the stress strain relationship is also in a linear, assumed to be linear in linear model. Whereas in non-linear model, at material level also, the stress strain relationship is non-linear, which is actually the realistic behavior of a particular material. The magnitude of displacement, change in the geometry due to displacement are assumed to be small and hence ignored. Right, so there is some secondary effect like geometry equilibrium, which is called a geometry non-linearity. Right, suppose if you consider the equilibrium in a linear model, we mostly consider the equilibrium in undeformed shape. But strictly speaking, the equilibrium should be considered in deformed shape, which is not there in your linear model. Whereas we will try to incorporate some of the features of deform equilibrium in nonlinear modeling. So again, there is a geometric nonlinearity. There may be a small deformation P delta or large deformation nonlinearity that we can consider. In large deformation nonlinearity, which is the most accurate one, we will consider the realistic response in a deformed shape. Realistic response in a deformed shape. So that is one of the difference. Material properties, we have already discussed this. In case of linear, they are linear. In non-linear, we will actually calculate the material properties based on some experimental data. And then we will use that material properties in our modeling. Reversibility in linear analysis, we will not assume that means the once you remove the load, the structure is completely reversible. The completely reversible means it will reach to its original position after you remove the load. Whereas in a nonlinear analysis, the final state may be different from initial state. That means there may be some permanent deformation which is there in the structure, which is called as a final state of the structure. Whereas in linear analysis, it will always be a initial position of the structure. Boundary conditions remain unchanged throughout the analysis. Here we can change the boundary condition. For example, let's say if you are modeling certain footing with certain element, so it has got certain contact area with the soil. Okay, so when you apply a lateral load on a particular element, this part will be lifted and there will be a compression on this part. So this portion of the soil, it loses the contact with the soil. That type of behavior can be modeled as a boundary condition in nonlinear type analysis, right? So this type of behavior you can also simulate by using boundary condition. That is possible only in nonlinear analysis. In linear analysis, we will assume that this entire surface is in contact with the soil always, whatever the load may be, right? So that is the boundary condition. Loading sequence is again in a linear analysis, the loading sequence is not important. For example, let's say you have got two loads. One is having magnitude of 50 kilonewton and another one is, let's say, 100 kilonewton. So whatever sequence you follow for application of the load, the final response of the structure will remain unchanged. For example, if you apply 50 kilonewton first and calculate the deformation, then you apply 100 kilonewton, calculate the deformation, add it, you will get the final deformation for 150 kilonewton, whatever the sequence of the loading may be. And this is not the case in case of your nonlinear analysis. The behavior of the structure may be dependent on the load history. So it depends upon these two factors, which load you apply first and the history of that particular load. That means which magnitude is applied at which time instant, and then accordingly the structure will react to your particular loading system. So analysis will extract that particular effect also. So loading sequence is not important. Here the loading sequence is also important. Then iterations and increment, load is applied in one step, single step. Here the incremental load can be applied with small increment with iterations, right? So that is the another difference. Computation type, computation time, of course, because the relationship is linear, the computation time is of course small in case of linear analysis. And due to many solution steps, in case of nonlinear analysis, your computation time is always high. And there are possibility that many times you will not get the proper result, expected result. And then user will have to interact with the computer, maybe for some input data to get the final solution. So that is for computation time. Robustness of solution can be easily obtained with no iteration from user. And here, as I told you, there is always you need to interact with the computer for various types of for time saving actually, because otherwise the program will keep on running because it is a iterative process, and then finally the solution will not converge, and then you need to find out the solution for this, and there are many options that you can implement to reduce this computation time and converge for the solution to converge, right? The use of results superposition and scaling is allowed here. That means superposition means it is very simple. Let's say if you have got a cantilever beam, and you apply, let's say, 2 kilonewton load on a particular beam and find out the deflection. Then you apply, let's say, on the same beam, apply 3 kilonewton load and find out the deflection. The superposition means the deflection due to 2 kilonewton plus the deflection due to 3 kilonewton will be equal to the deflection due to 5 kilonewton load. That is called as a superposition. That is applied in a linear type analysis only. And that's why this scaling of the result is possible. And whereas in nonlinear analysis, this factoring and scaling is not at all possible. So if you are observed in your computer model or ETAB model, once you run your case for primary cases, primary load cases, that may be dead load, live load, your response spectra load, or any other primary case, you need not to rerun those cases for combination. The combination, once you create the combination, these loads are automatically added. Analysis, again, analyzing this structure is not required. So even after the analysis also, you can put your combination in a linear model. Initial state of stress and strain. Initial state of stress is important. Here we assume that the structure actually, when we apply lateral load, the structure actually is means all material and all stresses are at zero condition. That means there is no initial stresses which is there in the structure. And here you can start your analysis with certain type of initial stresses already embedded in the structure, like for example, gravity load. And from that state of stress, you can continue your analysis procedure. That is possible. And that is important parameter as far as your linear non-linear analysis is concerned. Okay, so this is some difference between the linear and non-linear case. Now, as I told you, uh, the material behavior is non-linear. So let us look at some of the non-linear behavior of the material. The two most important material are concrete and steel, of course. So this is a compression testing for the concrete, and this is for steel, of course. Now you can observe here this behavior itself actually start from this nonlinear behavior actually start from this point. For our convenience, we assume that this is proportional up to certain limit, and then the nonlinearity is there. So this is a stress strain curve of concrete under compression load. So one more thing is the tensile capacity of the concrete is almost negligible. You can see here we have just assumed this much of the strain at the on the tension side, and then it collapse. So this is how this stress strain curve can be developed for the concrete. But there is a major difference between these two, that the confined and unconfined stress strain curve is different. So you can observe this red line indicates the unconfined stress strain curve for the concrete, and this blue line indicates the confined. What is confinement? That is nothing but if you test, let us say there is a concrete, and if you put some stirrups, that is lateral tiles, inside the concrete, and then there are longitudinal rebar. The behavior of the concrete in this particular region, which is outside this core area, or you can call a confinement zone, is different, and the behavior of the concrete inside this region is different. So this region, which is inside this particular region, which is called as a confined concrete, will always give you significantly high strength compared to the unconfined one. So this is how you can see this here. This is graph for confined concrete. It has got significantly high strength compared to the unconfined concrete. So that is one of the things that we need to understand for concrete also. Then for steel, there may be a cyclic behavior of the steel. So cyclic properties are also important, that we will see later on what is that cyclic behavior and hysteresis behavior. The types of the loading like monotonic loading and the single tone loading, all that we will see on the later stage. So this is how this concrete and steel will behave. These are most primary material that we are going to use for nonlinear modeling. So you first need to understand this behavior. Okay, so let us consider this geometric nonlinearity first. So what is geometric nonlinearity? That can be explained with the help of this simple example. This is taken from the Graham H. Powell group. Professor Powell, he has quoted this example in his book. So I have just copied from there. So I find it important to discuss so that you can understand the concept of geometrical nonlinearity. Okay, so what does this say? There is a single rod, let us say, with height equal to h, and it is pinned at the bottom, and then it is tied with the help of a spring, right? So and then there are two forces which is applied on the rod. One is the lateral force equal to h, and then the axial force equal to p. So definitely when you apply a force equal to h, there will be a force which is generated in the spring. So h is the lateral force, applied external force, and internal force in the spring will be equal to h. So this is the equilibrium condition when you consider this rod in undeformed shape. So undeformed shape equilibrium condition will be very simple. Force in the spring is equal to H. Now let us say this rod will deform with certain amount, let's say delta. Delta is the deformation of this particular rod under the action of the lateral as well as the gravity load. In that case, if you again applied equilibrium condition, but now in the deformed shape, previously what we have assumed is undeformed shape. Now here, if you apply equilibrium in the deformed shape, your force in the spring will be equal to H plus P delta over H, right? So that is the force in the spring. So it is changed now, right? So this is what you call the equilibrium condition. Now this is equilibrium in a deformed shape, and this will be the equilibrium in undeformed shape. Now, when you apply a equilibrium in a deformed shape, because this particular point will move from this position to this position, of course, there will be certain change in the length of the bar also. It will not be the original one. That is h, whatever we have assumed, that h will change, and there will be the change in the length of the bar, because there will not be it is not possible otherwise to maintain this position of this point horizontally, right? So the deformed length of the bar is given by this expression. You can calculate this length. That is nothing but h square plus delta square power 0.5, or root of h square plus delta square. So that is the deformed position of the bar. So first of all, this particular equation, what we are actually doing, this is called as the equilibrium relationship. This is called as the equilibrium relationship in undeformed or in the deformed position. And now we are also assuming that because this position is same horizontally, this particular node will move horizontally only, there will be the change in this particular length of this particular rod, and that is called as a compatibility condition or a continuity condition. So both should be satisfied, equilibrium and continuity. Now, again, when you extend this discussion further, you will find that this particular rod or this point will not move in a perfectly horizontal position, but it moves in a circular path. It moves with a circular path, right? So that also you can consider. That means this point, this position and this position is not same. It will change, so it will move in a circular path. So in that case, the force in the spring can be worked out as h plus p delta over h cos theta. That is the force in the spring, whereas the force in the bar is p cos P over cos theta. Okay, so there are three distinct conditions that we have considered. The first one is this one, where the equilibrium is considered in undeformed shape. Second one, the equilibrium is considered in the deformed shape, but we are now neglecting the circular movement of this particular rod. So that is there. And the third one, we are considering everything in the deformed shape as the movement, as per the movement. So this will be the most accurate one, the most realistic behavior of this particular deformation and under the forces. So based on this, there are three types of geometric nonlinearity. One is small displacement, where the equilibrium is considered in undeformed shape. One is P delta nonlinearity, where the equilibrium is considered in the deformed shape, but we are now neglecting the axial or the change in this position of this particular node. We assume that this load will move horizontally. So it is somewhat more accurate than this one. And the third one, where there is a large displacement analysis, we will actually analyze this particular movement, and we will also assume that there will be a movement in the form of arc. So this particular rod will move like this in the form of arc, like this. Okay. So this will be the most realistic one. So accordingly, you can classify the analysis type, geometric nonlinearity, in three types. One is small displacement analysis, second one is P delta analysis, and third one is large displacement analysis. The basic difference between all these three, you can see here. As far as the equilibrium is concerned, here for small displacement, it is undeformed position. For P delta analysis, it is always in a deformed position. And for large displacement, also deformed position is considered. But here there is a minor approximation while considering the deformed position. And that I told you that this will move in a arc, but we are assuming that there will be perfectly horizontal displacement. So that is an approximation in P delta analysis. Compatibility relationship, here we assume that it is linear, that is P equal to H. That means the force in the spring is equal to H. So there is perfectly linear relationship between force and this thing. Here also it is linear. Here also it is linear. But here you can see the force in the spring and force applied, the relationship is non-linear because it moves in an arc, right? Geometric nonlinearity, here it is completely ignored, is not considered. Here consider approximately. You can say we are considering the equilibrium in a deformed shape, but the nonlinearity, geometric nonlinearity is approximately considered. And here it is 100% considered. So that is the difference. So as far as the analysis is concerned, this one is the most accurate one, and this is the most complex analysis to perform. Whereas these two are simple. This is actually very simple compared to this one, but here you can approximately consider the geometric nonlinearity in the form of P delta. So the most of the time we perform this type of analysis, that is P delta analysis, where your geometric nonlinearity is approximately considered in the analysis. So what is the difference between material nonlinearity and geometric nonlinearity? The material nonlinearity has wide range of causes, many of which are poorly understood, and it is not governed by a single theory. So that is the drawback of material nonlinearity, whereas the geometric nonlinearity has clear clauses governed by a well-defined mathematical theory. As you can see here, we can always calculate this, but that doesn't mean that this particular procedure is simple. It is not at all simple. It is very complex procedure. Okay, so our knowledge of material nonlinearity depends mostly on the observations and experiment. So material nonlinearity, how we can incorporate in the model, that is basically dependent on our experimental data mostly. Even if there are certain codal references are there, Some international standards are there, but they are also based on the extensive experimentation. So material nonlinearity can only be incorporated once you have the experimental data with you. And there are a lot of data which is required at the material level, whereas geometric linearity has clear clauses, but it is difficult to implement, right? So geometric nonlinearity is not subject to judgment or interpolation. Nothing is required. But again, because you know that it is very difficult to consider this type of equilibrium in a deformed shape, and that's why the procedure is complex. So this is the difference between the material and geometric nonlinearity in short. Now, as far as this analysis is concerned, there are types of the analysis you can perform on your structure. This is based on the excitation, that is the application of the load, the type of the structure, and the response of the structure, right? So when you say static excitation are static, your load are static, structure is elastic, and your response is linear, that is linear elastic static analysis. Okay, so simplest analysis is this one, linear elastic static analysis. Very simple, because we are assuming that the excitation is static, structure is elastic, that means there is linear relationship, and then response is also linear. So it is the most simple one. And this one, last one, is most complicated one, right? So it requires many efforts to do this type of analysis, which is load, that is your excitation is dynamic type, structure is inelastic, which is actually realistic structure, and the response is also non-linear, that is force deformation relationship is non-linear. So non-linear inelastic dynamic analysis is the most complicated one, and that we are trying to do in a performance based design. Not exactly every time we need to do this type of analysis, but that is one of the step in performance based design of the structure. Okay, so let's understand this equilibrium equations for different types of analysis. When you say linear static, it is always F is equal to Ku. K represent the stiffness and U is your deformation. So force is directly proportional to stiffness times deformation. So that is a simple form of equilibrium equation, which is used as linear static. When you say linear dynamic, that means the force what we get is it dependent on the time. So whenever you say dynamic, it is always a t component which is introduced in the equilibrium equation. And mu double dot, this is your mass matrix, then your damping matrix and stiffness matrix, all dependent on t. So because the loading is dynamic, when you say dynamic, it t factor introduced. So that is the linear dynamic equilibrium governing equilibrium equation. Non-linear static, again, it is a non-linear, the force is non-linear. So this non-linear force is introduced here, which is less than your linear assumption. Okay, you can see here, this one is your non-linear force. So Ku minus F non-linear equal to F. That will be the equilibrium equation for non-linear static. And the last one, the most complicated one, is nonlinear dynamic equilibrium equation. The force is also nonlinear. It is also a time dependent, that is dynamic force. And your relationship for all these terms are dependent on the time. That is dynamic relationship, right? So nonlinear dynamic equilibrium equation is this. Okay, now let us concentrate on how this stiffness is work out for a particular structure. Okay, so the stiffness thing actually start at material level. So material level means there are two properties of the material, that is E. So E is the thing which will give you the material stiffness actually. Okay, so it start at material level. So once you define the relationship between stress and strain, that is nothing but the E. E is non-linear. You are making this E, that is Young's modulus, as non-linear, and then you are capturing the material stiffness, right? Now this material stiffness will finally form the sectional stiffness. Okay, so once you define your material as nonlinear, using that nonlinear properties of the material, the the sectional stiffness is formed, which is your A and I, that is inertia of the section and area of the section and other properties of the section if you want, right? So material, it start with material stiffness, and then the sectional stiffness matrix will be formed based on the material stiffness. And from material level, using the sectional stiffness, the member stiffness will form. That is your L, that is length, right? So you should know this A and I to form this material stiffness. You should know the E variation with your stress strain variation to form the cross sectional stiffness. So all are dependent. So it always start with the material level and ends at the structure level. So when these members are connected together, they will form the structure, and that will form your structure stiffness. Okay, so accordingly, the level wise, if you classify, once you define the your stiffness at material level, the nonlinear relationship at material level, it is automatically incorporated in all other levels. It is automatically incorporated in all other levels for forming the sectional stiffness, for the member stiffness, or then ultimately to build a structural stiffness, right? So this is very primary level of the stiffness where the material property itself is nonlinear, and once you got that nonlinear relationship between the force and deformation at material level, you can always build a stiffness matrix for the structure, considering all other factors at member level also, right? So that is how the stiffness is formed for the particular structure. Now, the question is how to incorporate this nonlinearity in our model, because simulating the nonlinear response is not an easy job, right? So there are number of ways to incorporate the nonlinearity. Okay, so the first method is you do the experiments. That means you should have the experimental data at material level. For example, let's say you have performed the experiment for stress versus strain for a particular material, stress strain relationship for a particular material, and that will be a nonlinear relationship. This is at material level. Okay, then you can perform the experiments at the component level itself, that is at the member level. That is, for example, let's say you have a relationship between m theta, right? That is moment rotation relationship, or maybe m phi, which is your moment curvature relationship. Okay, so these are the relationship at the member level, and this is the relationship at material level. So one way of incorporating the material the nonlinearity into the model is you just find out all this relationship. Now m theta and m phi is again different. So what is this is actually I will tell you. Let's say if you have a beam and it deforms with this shape, okay, and then if you draw a tangent, this is your theta, right? And moment will be bending moment, right? So m theta relationship is this. Now, when this beam will deform, it has got a curvature also, and this is phi, that is curvature. So either you can define this phi, so m phi relationship, or maybe m theta relationship. So moment rotation or moment curvature relationship. That is at the member level, right? So that is the second way of incorporating the nonlinearity. Now the question is where we can get all this relationship, where we can get all this relationship to be incorporated in our computer model, because otherwise your model will be always linear, because we are assuming the linear thing otherwise, right? So where we will get all this relationship, that is a big question. So there are three ways of getting this relationship. As I told you, one common way is experimental base. The first one is experiment. You perform the experiment, you apply different types of the loading, get different types of relationship. This is not the only relationship. As I told you, there is a lot of change in the behavior for monotonic loading and then cyclic loading also, and then hysteresis loading, right? So hysteresis behavior is again a very important data. along with the monotonic behavior. And again, for the concrete, if you say the confined moment relationship is different for the confined concrete is it different, and for non-unconfined concrete, the relationship may be different. So you perform all this experiment on a sample model, build all this relationship curve, maybe at the material level or maybe at the member level. Okay, so that is the first way of getting this data. The second way is use inbuilt standards, like for example ASCE. So ASCE has got already inbuilt all this relationship. ASCE 41, if you look at this particular standard, you will get all this relationship between for concrete as well as for steel. Use this ready-made curves for various types of the relationship for hysteresis behavior or maybe cyclic behavior or whatever monotonic behavior. So this is already inbuilt. You can get all data from this code. But again, as I told you, or whatever things you will get from this particular standard or this particular reference manual, that is again based on the extensive experiment. So they have already carried out all this extensive experimentation, and based on that, there are certain recommendations that you can use. There are other standards also like FEMA. FEMA guideline is there for federal emergency management, and then there are ATC also. So there you can get this all this relationship. So that is the second way of obtaining this relationship. The third way is you analyze this particular component level at the component level. That means what? You select one of the special component, maybe beam or maybe column, and analyze it by at the micro level in the computer model. Analyze it micro level means you model everything in that. Maybe you can go for the solid type modeling, finite element modeling, as I told you, quantum modeling for a single member, not for the entire structure. That will be the difficult. Okay, and then using that component level model, that is a single model for a single element, you find out all this relationship. So that is the third way. That is the computer model, but at the micro level. This computer model is at the micro level. So these are the three ways of getting this nonlinear relationship between different at the material or at the component level. Okay, so this is about how we get the nonlinear relationship. Now let us move ahead, and then we will see what are the different types of model which is available after getting this nonlinear relationship. What are the different models which is available in ETAB to incorporate this nonlinear behavior? The first model, which is actually a physical model, is called as quantum model, right? Continuum model, right? So here what we do is we will actually divide our entire element into the finite elements, small elements, right? So of course, when you do that, you are using the finite element method, and that is the most accurate one. Okay, and then it will explicitly incorporate all material as well as component level nonlinearity. Okay, so it is explicit model for capturing the nonlinearity, but that is very difficult to build, and you can understand because we are using the FE method, so it is always difficult to get the solution. It will take a huge time also, right? But the thing is, all types of nonlinearity can be captured with the help of this continuum model. So that is the first way of modeling your nonlinear behavior. The second way is called as distributed elasticity, which is also called as fiber type modeling. Now, what we are doing is here, we are not considering this entire element as a nonlinear one. So we are going at the member level. For example, let's say this is a column, and you have got let's say the cross section of the column is like this with certain reinforcement inside it, right? So what we are doing is we are modeling the fiber to represent